Also, when we're looking at energy, we need to talk about the term of enthalpy. So we looked at specific heats and the amount of heat it takes to warm up a certain type of material. We also look at calculations in enthalpy, and enthalpy are the heat changes due to a chemical reaction. So these things we've already kind of talked about before. We can have exothermic reactions that release heat, or endothermic reactions where heat has to go into the reaction. First, let's look at this exothermic energy level diagram, and let's try to interpret it a little bit. So one reaction we had hydrogen gas reacting with oxygen gas. In the lab, this is our splint test where we test the gas coming off, and it reacts to make water, H2O. Now, if I balance this equation, we have an equation something like this. Well, these are my reactants. They're up here. And notice they have a certain level of potential energy in those reactants. When this reacts, the products, the water, has a lower overall potential energy. So the energy of our reactants goes down from H2 and O2 reacting here. The overall energy goes down to making our product water. So water, a couple ways we can look at this. Water is more stable as far as a chemical compound than hydrogen and oxygen independently, but more importantly, its overall chemical potential energy is lower. What that means is when it reacts and the overall potential energy is lower, this has to release heat in the reaction. Energy is the difference here. And that difference, notice, is represented as a change in H. H being our term enthalpy. So its enthalpy is H. So the change in H is the difference between the reactants and the products. And we can write an equation for it. The change in enthalpy is the enthalpy of the products minus the enthalpy of the reactants, if we want to write an actual chemical equation. Now notice this graph has something else in it. It has what's called an EA, activation energy, and we'll get to that later. This is really the spark that causes it to happen. So most of these energy level diagrams, there is a little bump to get the reaction going, to collide the molecules with with the appropriate level of energy so that they actually react and go to making our products. So if we turn this around the other way, if we take H2O, well, we could take H2O, we could add a certain level of heat, a certain level of energy, and we could break it apart into its elements, hydrogen and oxygen. So hydrogen and oxygen being up here as our products in this reaction, and our reactant now being water. Well, to do this, we have to put in a certain amount of energy. That amount of energy, again, is our change in enthalpy. And what we'll notice is if we look at these equations independently, here is our hydrogen and oxygen reacting to form water. And notice this is the amount of energy, the exact amount of energy that's released per mole in this balanced chemical equation. So we have 2 moles of hydrogen reacting with 1 mole of oxygen to make 2 moles of water. This is the amount of energy that's derived from that reaction. Now notice if we change the amounts, they're doubled. So we had 2 here, we double it to get 4, 2 and 4 here. Notice if we double it, well, that's going to double the amount of energy that's given off. Likewise, if we calculate it per mole of water, then we'll have the energy that's produced per mole of water. And again, it is exothermic. Anytime we see heat on this side of the equation, think of it as a product. It is a product of the reaction. This heat came out of the reaction. Okay, or the level of energy. Okay, so if we take that endothermic reaction and we look at it, so now I have the endothermic reaction. So notice this was hydrogen plus oxygen yielding water. Now notice, if I flip that reaction around where we have water and we add energy to break it apart into its elements, notice this value of energy, 483.6, is exactly the same as this amount of energy. So if we flip a chemical equation around, the amount of energy that is released in a certain exothermic reaction, well, if you can flip that reaction around, that amount of energy needs to go in to again, in this case, split the molecule back down. So the energy is conserved, and that's an important thing to know when we go on to do Hess's law calculations, is that if we flip a reaction like this, well, we also flip and put the energy on the other side. Now in this one, my change in enthalpy is going to be that 483.6 kilojoules per 2 moles of water to take that water, break it apart into the elements hydrogen and oxygen. Now we might want to notice that normally we don't write our thermochemical reactions with the energy in the balanced equation. If we're doing Hess's law stuff, we do. Otherwise, often it's reported as a value, as a change in enthalpy per mole. Now notice we have lots of these values. So these are particular enthalpy values. These are enthalpies of formation. Now notice the symbol is very specific here. So change in enthalpy of formation, that's what the F is for. And the little O that's a superscript here stands for at standard conditions, which is 298 Kelvin and 1 atmosphere. So we're working at standard conditions. So at standard states, these are the enthalpies of formation. Well, what's the enthalpy of formation for these products? Well, it's forming these products from their elements in that standard state. So if we just take, well, let's take ammonia. So ammonia, it says to make ammonia, it's negative 46.19. Ammonia, its elements that it's made out of is nitrogen and hydrogen, both of which are gases at normal, again, room temperature and pressure, to make ammonia. Okay, so to make ammonia, and we'd have to write a balance equation. This is where it gets a wee bit tricky, because all of these values are per mole. So the change in enthalpy of this reaction is the negative 46.19 kilojoules per mole. So it's forming that compound from its constituent elements at standard conditions. Or, this is maybe a better definition, the standard enthalpy of formation, again denoted by the symbol, is the enthalpy of change for the formation of 1 mole of a substance in its standard state from its component elements in their standard state. And again, so that means at room temperature, if hydrogen is gas, then it's from forming it from hydrogen gas. If, say, we're making sodium chloride, and we want to write the equation for the enthalpy of sodium chloride, well, sodium is a metal, it would be a solid. Chlorine is a gas. And again, one thing we have to be careful of is if we have that value, do they have sodium chloride on this chart? I believe they did. Right here, sodium chloride. Notice sodium chloride negative 410.9. So the change in enthalpy of formation is negative 410. That's kilojoules per mole. And it's per mole of product. So if there's a 2 here, this really isn't the correct reaction or equation for this reaction. We'd have to cut it down and say sodium plus 1/2 chlorine equals sodium chloride. And for that 1 mole of this product, this is the amount of energy that would be, notice it's negative, so it's an exothermic reaction, and this amount of energy would be released in that chemical reaction.